Now we will understand about the specific heat capacity and the calorimetry. The specific heat capacity is defined as the amount of heat required to raise the temperature of body by 1 degree per unit mass. It is called the specific heat capacity. The amount of heat required will be mc delta T. Here C is the specific heat capacity, m is the mass of object, and delta T is the change in temperature. From this we can write C is equals to Q upon m delta T. So the specific heat capacity is independent of mass. So its value depends only on the nature of material and the temperature change. The SI unit of specific heat capacity will be, SI unit of Q will be joule per kg Kelvin, but the most used unit is calorie per gram degree Celsius. The molar specific heat. If instead of mass we find specific heat required per mole, then it will be molar specific heat. It is amount of heat required to raise the temperature of 1 mole of a substance through 1 degree Celsius. It is denoted by capital C, that is equals to heat required per unit mole to change the temperature by 1 degree Celsius. So its unit will be joule per mole Kelvin. Heat capacity is the amount of heat required to raise the temperature of the body by 1 degree Kelvin or 1 degree Celsius. It is denoted by C dash, that will be equal to heat required per unit change. The value of C is Q by m delta T. So we can write C dash is equals to m into C. The SI unit of the heat capacity will be joule per Kelvin. The value of heat capacity depends on material as well as the size or shape of the object. Now let us understand what is the meaning of water equivalent. If the heat capacity of a body is expressed in terms of a mass of water, it is called water equivalent of body. Water equivalent of a body is the quantity of water whose temperature would be raised through 1 degree Celsius or 1 Kelvin by the same amount of heat as required to raise the temperature of body through 1 degree Celsius or 1 Kelvin. Let's say W is the water equivalent of body of mass m and specific heat capacity C. Then W into C of water into 1 is equals to m into C into 1. So W will be equal to mc divided by C of water. Specific heat of water is 1 calorie per gram degree Celsius. So we can write W is equals to m into C. In SI system, specific heat of water is 4200 joule per kg Kelvin. So W will be equal to mc divided by 4200. W is measured in gram in CGS unit and in kg in SI units. Now let us understand the latent heat. It is the amount of heat required to change the state of unit mass of substance at constant temperature. Here focus on this word, at constant temperature and pressure. So Q is equals to M into L, where L is the latent heat. So L can be written as Q upon M. SI unit will be joule per kg or calorie per gram, also we can use. The latent heat is the amount of heat required to change the phase. For example, to convert water to ice or ice to water. This conversion will always take place at 0 degrees Celsius only. When 0 degrees Celsius ice is converted into water, the temperature will not change. So 0 degree ice is converted into 0 degree water and vice versa. Same way, when water and steam are converted, then temperature is not changed. That means water is converted into steam at 100 degrees Celsius, and after condensation steam is converted into water, that is also at 100 degrees Celsius only. Now, let us remember some values. For water, specific heat capacity is 1 calorie per gram degree Celsius. The latent heat of fusion is 80 calorie per gram. The latent heat of vaporization is 540 calorie per gram. And specific heat capacity of ice is 0.5 calorie per gram degree Celsius. Now, based on the quantities that we have learned about heat, that is specific heat, molar specific heat, latent heat, etc., let us understand the calorimetry. As we know that heat is a form of energy and as such is a measurable quantity. Calorimetry deals with the measurement of heat. The vessel which is largely used in such measurement is called calorimeter. The principle of calorimetry. When two bodies of different temperatures are allowed to share heat, they attain a common temperature. If it is assumed that there is no heat received or given to any body outside the system, and if there is no chemical action involved in the process, then we can say heat gained is equals to heat lost. This simple statement is based on the conservation of energy. And it is called principle of calorimetry. The different units of heat that are used are joule and calorie. 1 calorie is equals to 4.186 joule and 1 kilocalorie will be equal to 4.186 joule. Now let us see how the change of state occurs in the case of water. Depending on the temperature and pressure, all matter can exist in a solid, liquid or gaseous state. These states or forms of matter are also called the phase of matter. It is possible to change the energy of these molecules by supplying heat, which in turn can result in change of phase. Let us illustrate this point by considering three phases of H2O molecules: ice, water and steam. Let us illustrate this point by considering a container 1 kg of ice. At temperature minus 25 degrees Celsius. This figure is a graph which shows the changes in the state of ice with time as more and more heat is added to it. Now, let us see the graph step by step. As the ice is initially at minus 25 degrees Celsius and its specific heat is 0.5 kilocalorie per kilogram degree Celsius, its temperature increases by 2 degrees Celsius per kilocalorie of heat supplied. At 0 degrees Celsius, the steady temperature rise stops and the ice starts melting, and consequently a point A on the curve corresponds to the melting point of ice. From A to B, the temperature remains at 0 degrees Celsius. As it is melting, we are changing the phase, and change of phase always occurs at constant temperature. In this, we have to add more 80 kilocalorie. This is the amount of heat to be melt 1 kg of ice at 0 degrees Celsius to water at 0 degrees Celsius. This change is indicated by this horizontal line AB. Thus, a phase change has taken place from solid to liquid without change in temperature. The heat supplied is used to increase the energy of molecules so that they can break loose from their bonds in the solid structure and change into liquid. When all the ice has turned into water, the temperature rises once again as we have continued to supply heat. Since the specific heat of water is 1 kilocalorie per kg degree Celsius, there is now rise of 1 degree Celsius per kilocalorie heat supplied. This rate of change is less than that of ice, so the slope of graph BC is smaller than slope of graph OA. The point C corresponds to the 100 degrees Celsius, that is the boiling point of water. When 100 degrees Celsius is reached, the temperature again stays constant despite further heating until the total 540 kilocalorie is added. This is the amount of heat needed to vaporize 1 kg of water at 100 degrees Celsius. To steam at 100 degrees Celsius. So at point D, it has been converted into steam. And point B, the ice has been converted into water. Now, the heat supplied is again being used to break the loose molecules of water into free molecules in the gaseous steam phase. When all the water has become steam, the temperature increases again. The specific heat of steam is 0.48 kilocalorie per kg degree Celsius. So the temperature increases by 2.1 degrees Celsius kilocalorie of heat supplied. The portion of the graph which represents the change in state as a steeper slope than those of position OA and BC corresponding to the ice to water. Now, let us understand the pressure temperature diagram and the triple point. A graph between pressure and temperature of a substance is called PT diagram. This diagram is also called a phase diagram since all the three phases are separated from each other by three lines. In this figure, we have drawn the phase diagram A and B for two specific substances, namely water and CO2. This is for water. In order to arrive at the concept of a phase diagram, we should understand the vaporization curve, the fusion curve, and the sublimation curve. The boiling point of a liquid also depends upon the pressure. The curve OC shows how boiling point of water varies with pressure. A curve which shows the variation of boiling point with pressure is called vaporization curve. So the curve OC is vaporization curve. In this case, this OC line is also called the steam line. The points on this curve represent the states in which liquid and vapor phase coexist. The upper limit C of this curve occurs at temperature of 374.14 degrees Celsius and a pressure of 218 atmospheric pressure. It is known as the critical point. A substance cannot exist in a liquid state at a temperature above that of critical point, regardless of how great the pressure may be. Helium has the lowest critical temperature, minus 268 degrees Celsius, and is therefore a gas at all the temperatures above that. The melting point of solid also depends upon the pressure. A curve which shows the variation of melting point with pressure is called the fusion curve. Here, OB is the fusion curve. In case of water, this curve is called ice line. It is to be noted that this curve leans slightly towards the left. This implies that the pressure is increased, melting point is lowered. As we increase the pressure, the melting point is lowered. This behavior of ice together with gallium and bismuth is unique as melting point of all other substances increase with increasing pressure. The fusion and the vaporization curves of water intersect at a temperature of 0.01 degrees Celsius and at a pressure of 0.06 atm. Along the fusion curve, both ice and water can simultaneously exist. Hence, under conditions corresponding to those of intersection of these three curves, the solid, liquid, and gas can exist together. This intersection is accordingly called the triple point of water. So, this O point is the triple point of water. In case of water, this curve is also called the Horforst line, and that is shown by OA. At atmospheric pressure, the addition of heat causes ordinary ice to melt. since the triple point of water is at 0.006 atm, which is below 1 atm, but the addition of heat causes solid CO2 sublimate since the triple point is at 5.11 atm. So, from all the knowledge we have seen, let us define the triple point. The triple point of a substance is that point on the PT diagram or phase diagram whose coordinates gives the particular temperature and pressure at which the solid, liquid and vapor phases of the substance coexist. But they should coexist in equilibrium. Without any change in their proportions. So, at the triple point of water, there will not be any phase transformation from ice to water, or from water to ice, or from water to steam, or steam to water. Now, let us see some examples based on the principle of calorimetry. In this example, 5 gram of ice at 10 degrees Celsius is mixed with 1 gram of steam at 100 degrees Celsius. We want to find the final temperature and the composition of mixture. The meaning of composition of mixture, that means the final liquid would have ice water, only water, or water steam. We want to find that composition. Here we will use the principle of calorimetry, that is heat lost is equals to heat gained. Here heat lost will be by steam and heat gained will be by ice. So first of all, let us find the maximum heat lost by the steam. First, we have steam at 100 degrees Celsius. So steam will convert into water. So from steam to water. Steam at 100 degrees Celsius to water at 100 degrees Celsius. For that we require latent heat, that is Q is equals to L into M. The latent heat for vaporization is 540 into mass is 1. So that will be 540 calorie. Now, after that we have water at 100 degrees Celsius. Now, the heat gained by ice to melt, as it is at 0 degrees Celsius, it will simply melt. So it will require also latent heat, that will be equal to L into M. The latent heat of fusion is 80 into mass 5. That will be 400 calorie. So after this conversion, we have water at 100 degrees Celsius 1 gram, water at 0 degrees Celsius 5 gram. an additional heat of 540 minus 400, that is equals to 140 calorie. Now again this water will lose some energy. So energy lost by 1 gram water at 100 degrees Celsius. Q is equals to mc delta T. So 1 into delta T 100. So Q will be equal to 100 calorie. After that we will have water of 5 gram at 0 degrees Celsius. So in total we have water 5 plus 1, that is equals to 6 gram at 0 degrees Celsius, and total energy 140 and this 100 calorie, that is equals to 240 calorie. This much amount of heat will be used to change the temperature of total of 6 gram object. So Q is equals to mc delta T. Q is 240, mass will be total 6 into 1 into delta T, that is T minus 0. So T will be equal to 40 degrees Celsius. So finally we have 6 gram water at 40 degrees Celsius. So this will be our final answer. In this example, 100 gram of ice at 0 degrees Celsius is mixed with 10 gram of steam at 100 degrees Celsius. We want to find the final temperature of composition. Again, we will use the principle of calorimetry, that is heat loss is equals to heat gain. The heat loss will be by the steam. So let us say first find the heat lost. The steam at 100 degrees Celsius will be first converted into water at 100 degrees Celsius. By doing so, it will release the energy, that is equals to Q is equals to L into M. The latent for vaporization is 540 into mass is 10 gram. So that will be 5400 calorie. After doing this, we have water 10 gram at 100 degree Celsius. Now ice will gain that energy to melt. So we will have ice at 0 degrees Celsius to water at 0 degrees Celsius. For that we require latent heat, that is equals to L into M. Latent heat of fusion is 80 and mass is 100, that is equals to 8000 calorie. Here this is not the enough amount of energy that we have. Now if this water is converted from 100 degrees Celsius to 10 degrees Celsius, that is water at 100 degrees Celsius to water at water at 0 degrees Celsius, it will release heat is equals to mc delta T. The mass is 10, C is 1 and delta T is 100. So Q will be equal to 1000. So total heat released will be equal to 5400 plus 1000, that will be equal to 6400 calorie. Now the amount of heat required to melt the ice is 8000 calorie. We don't have that much amount of heat, so we won't be able to melt the ice completely. So let us find how much of ice will melted. For 10 gram, or we can say in 80 calorie, we can melt 1 gram. Then how much of ice we can melt in 6400 calorie? So M will be equal to 6400 divided by 80. So M will be equal to 80 gram. So we will able to melt only 80 gram of ice. So in the final composition, we have 80 gram water at 0 degree Celsius by melting of ice. We have 10 gram water at 0 degree Celsius by the condensation of steam, and we have remaining 20 gram of ice. So final temperature of the mixture will be 0 degree Celsius. Total we will have 90 gram water and 20 gram ice at 0 degree Celsius. So this will be our final answer. In this example, 30 gram ice at 0 degree Celsius is mixed with 25 gram of steam at 100 degrees Celsius. We want to find the final temperature and composition. Again, we will use heat lost is equals to heat gained. Here, heat will be lost by 25 gram of steam at 100 degrees Celsius. First, it will be converted into water at 100 degrees Celsius. By doing so, it will release some heat, that is equals to Q is equals to L into M. So 540 into 25, that will be equal to 13500 calorie. Now, heat required to melt the ice is Q is equals to L into M. The latent heat of fusion is 80 and mass is 30. So heat energy required will be 2400 calorie. So after doing this, heat remaining is equals to 13500 minus 2400. That will be 11,000 and 1100 calorie. So after this, we have water at 100 degrees Celsius, water at 0 degrees Celsius. This water is 25 gram, this water is 30 gram, and this much energy, 11,100 calorie energy. This is enough energy, so steam will not further water will not further lower its temperature, but this water at 0 degrees Celsius will gain the energy. Now let us find the energy required for 30 gram water at 0 degrees Celsius to move to 30 gram water at 100 degrees Celsius. The heat energy required will be mc delta T. So Q will be equal to mass is 30, C is 1, and delta T will be 100. So Q will be equal to 3000 calorie. So from this 11,100 calorie, this 3000 calorie will be used to change the temperature of 30 gram water from 0 degree to 100 degree. So now energy remained will be 11,100 minus 3000, that will be equal to 8,100. Now, finally, we have total 55 gram of water at 100 degrees Celsius and 8,100 calorie of energy. This much energy will convert some of the water into steam. So, amount of steam will be equal to 8100 divided by 540, that will be equal to 15 gram. So from this total 55 gram, 15 gram will be steam at 100 degrees Celsius and 40 gram water at 100 degree Celsius. So this will be our final answer. After seeing these three different examples, let us note down the summary. First point, when ice is dominant, that means ratio of mass of ice upon mass of water is 8:1, is greater than or equal to 8:1. Then the entire steam will be cooled up to 0 degree and the final temperature will be 0 degree. Excess of 8:1 ratio ice will be left and will have ice water mixture. So if mass of ice upon mass of water is equals to 8:1, then we will have water at 0 degrees Celsius. So equilibrium temperature will be 0 degrees Celsius. If mass of ice upon mass of water is greater than 8:1, then we will have the mixture of ice and water. The second case, when steam is dominant, that is the mass of steam to mass of ice is equals to 1:3, then ice will be heated up to 100 degrees Celsius water. So final temperature will be, we have water at 100 degrees Celsius, and when mass of steam upon mass of ice is greater than 1/3, then we will have a mixture of steam and water. And the third case, when ratio is between 8:1 and 3:1, then we have to find the conventional calculation, and the equilibrium temperature would be between 0 degrees Celsius to 100 degrees Celsius. In this example, liquids A and B are at 30 degrees Celsius and 20 degrees Celsius. When they are mixed in equal masses, the temperature of the mixture is found to be 26 degrees Celsius. We want to find the ratio of their specific heats. We can use the principle of calorimetry, that is heat lost is equals to heat gain. Here liquid A is hot body, so it will lose some heat. So mass of A into specific heat of A into delta T, that will be equal to 30 minus 26 is equals to mass of B into specific heat of B into 26 minus 20. Given they are added in equal mass, this will get cancelled out. So Ca into 4 is equals to Cb into 6. So Ca upon Cb is equals to 3 by 2. Let us see the next example. Suppose you want to cool 0.25 kg of cola at 25 degrees Celsius by adding ice initially at minus 20 degrees Celsius. How much ice you should add so that the final temperature will be 0 degrees Celsius with all ice melt? Given the specific heat of ice is 2000 joule per kg Kelvin and specific heat of cola is 4160 joule per kg Kelvin. Here cola is the hot body, so heat lost by cola will be equal to mc delta T, that is 0.25 into C is 4160 into delta T will be 25. So we will get the answer 26,000 joule. Now let the mass required is m ice. Then the heat needed to move it from minus 20 degrees Celsius to 0 degrees Celsius is Q1, that is equals to mc delta T. So mc of ice is 2000 into 0 to 20, that will be equal to 20. So this will be 40,000 m. Now heat needed to melt the ice. Will be equal to L into M, that is equals to M into 3.34 into 10 power 5 joule per kg. So energy gained by ice will be equal to M into 3.74 into 10 power 5, and that should be equal to the heat lost. So 26,000. So M will be equal to 0.07 kg. So M will be equal to 70 gram. In this example, a bullet of mass 10 gram moving with speed 20 meter per second hits an ice block of mass 990 gram kept on a frictionless floor and gets stuck in it. How much ice will melt if 50% of the lost kinetic energy goes into ice? The 50% of lost kinetic energy is equals to mc delta T or L into M, because initially it was at 0. So L into M is equals to half of half m v square. So 80 into 4.2 into M, we want to convert this into joule. So 80 into 4.2 is equals to 1 by 4 into 10 into V square, that will be 20 into 20 divided by 1000, converting this 10 gram into kg. Simplify this, we will get the answer M is equals to 0.003 gram. So this much amount of ice will be melted. In this example, heat is being supplied at a constant rate to the sphere of ice, which is melting at a rate of 0.1 gram per second. It melts completely in 100 seconds. We want to find the rate of rise of temperature thereafter. That means after melting, what will be the rate of rise of temperature? Here dq by dt is equals to dm by dt into L, because q is equals to m into L. So dq by dt is equals to 0.1 into 80, that is 8 calorie per gram second. Now q is equals to mc delta t. So dq by dt is equals to mc dt by dt. This is rate of change of temperature. Given dq by dt is equals to 8, mass we have to first find the mass. 0.1 gram per second is melted. So in 100 seconds, 0.1 into 100, that will be 10 gram of ice is melted. So mass will be 10 into C will be 1 by 2. Sorry, it is converted into water. So 1 into dt by dt. So dt by dt will be equal to 0.8 degrees Celsius per second. So after melting the ice, the rate of change of temperature or rate of rise of temperature will be 0.8 degrees Celsius per second. Let us see an example on water equivalent. In a calorimeter of water equivalent 20 gram, water of mass 1.1 kg is taken at 288 Kelvin. If steam at temperature 373 Kelvin is passed through it and temperature of water increases by 6.5 degrees Celsius, then we want to find the steam of the mass of steam condensed. Let's say mass of steam condensed is x gram. So heat released by steam will be equal to 540 into x plus, it will also change the temperature. Its temperature will decrease by 6.5 degrees Celsius. So this will be mc delta t, mass will be x, c is 1, and delta t will be 78.5. Now this much amount of heat will go in water as well as calorimeter. So Q required by water is equal to 1100 into 1 into 6.5, that is equals to 7150 calorie, and the heat energy required by the calorimeter is equals to 20 into 1 into 6.5, that is 130 calorie. So Q released is equals to Q gained according to the principle of calorimetry. So Q released will be 540x plus 78.5 x is equals to 7150 plus 130. Simplify this, we will get x is equals to 11.7 gram. So this much amount of steam will be condensed.